Спасибо большое. Okay. I'm very glad to start our next lecture. I recall you that currently at the modern dynamical systems we are focused on homogeneous dynamics, and our first lecture that happened last week was a very introductory one, so there was a lot of discussion who are the lattices, but basically we did not do any dynamics. We only studied groups from some kind of measure theory point of view, and tried to combine these two subjects that maybe appear to be very different in your head, like geometry of groups and measure theory. And now they meet at the same point. So today it's time to introduce another ingredient, and actually we will prove a theorem that will lead us to some dynamical results about the dynamics of action of some groups. So our goal for today is called the Hobby-Moore ergodicity theorem. But once again, as usual, you will need to be patient, because at the very beginning, you will see things that will look as more algebra and measure theory, and only at the second half of the lecture, you will actually understand why dynamical systems are somehow introduced there. Just, sorry, one more urgent question. No, okay, it's not urgent. So, our goal for today is named after Hobby and Moore. Hobby-Moore ergodicity theorem. We start with the discussion of group actions and representations. So our plan is as follows. First we do this, then I state the main result. I prove this result in a low-dimensional case. Then we state Hobby-Moore theorem. Low-dimensional, I mean that I will prove the theorem for the case of SL2R. Then I will state the result for SLDR and explain you how the most general version of this theorem will look like. I'm not going to prove it. The proof will be only for SL2, as on the previous lecture when we were concentrated on the case of SL2R, but we announced that a similar statement is true for any dimension. We do the same. Then I give you the statement of this theorem in the most abstract way, and then we discuss briefly some dynamical consequences of this theorem. So we take triple. It's a probability space. It's a space. It's a sigma algebra, and it's a probability measure. So it's only probability space. And we consider the set L infinity. I don't know if you had any functional analysis course. In case you are probably familiar with this guy. If not, it's just essentially bounded measurable functions. And this space is the dual to L1, which is a class of integrable functions. So due to this fact, we understand that it should admit a weak topology, weak star topology. This is a star. But at the same time, it's not true that this space is necessarily separable. So I introduce a very important definition that plays some crucial role in measure theory. I will call it a Lebesgue probability space. if, okay, not maybe the whole space, but at least some part of it that is dense inside is separable. So if it contains a separable weak star dense subalgebra, which separate points. What does it mean to separate points? It means that we always have a measurable set X, E, as a subset of X, such that it has a full measure. And for any X and Y that do not coincide, there exists F, a member of the set of function, such that it knows that X and Y is not the same point. That's what it means to separate points. Understand? So then you may ask yourself, how natural is this notion? Is it true that we see them very often, these Lebesgue probability spaces? And the next question is, what can we say about them? Why they are cool? Why do we care about them? So let us put the following proposition. Let's answer on the first question. How often can we see them? So we take X, and we put some restrictions on S. On X, mainly, I want it to be locally compact. Second countable space. B will be a Borel sigma algebra. And mu is a Borel probability measure on X. Then we claim that this triple forms a Lebesgue probability space. I'm not going to prove it very formally, but in general, the proof is very constructive. We have to present such an A that would satisfy the conditions in the definition, right? We need to explicitly show who is the set A. And in this case, we just take the image in L infinity, the algebra of bounded continuous functions on X. So we take bounded continuous function, we consider their image in L infinity, and I claim that it's good enough as a set S, as a set A. So it's easy to check that all the conditions about the separability, density are satisfied, and the fact that we can always distinguish it with some function, it's also not that hard. So they exist. These Lebesgue probability spaces, they exist and they are not that rare. Now, the next point is that we take X A mu. It's this Lebesgue probability space. The next point should answer my second question. Why it's so cool to have them? Why do we spend our precious time discussing it? So we fix such a space, And then I claim that there exists T from 0 to, that belongs to the interval from 0 to 1, such that this probability space x a mu is isomorphic to disjoint union of 0t equipped with the restriction of the Lebesgue measure. Of R and of N, and a measure of mass 1 minus T. So this looks very technical, but morally it just says that up to atoms and to isomorphisms, it exists and it's unique. So basically we have just one Lebesgue probability space, which is formed by disjoint union of intervals, and we just put in a smart way the measure there, which is some natural Lebesgue measure. So now we can switch to the study of the group actions on these spaces. And that will be our plot for the next several minutes. One more definition. So we have a Lebesgue probability space. And we had the locally compact group. So we consider a measure preserving action of G on X. So what is it? So we want that we act by G on X, and thus this map is measurable, and that for any G, any element of the group, the map that takes X to the result of the action preserves mu. This map is the one that takes X to X. So probably we'll need some example of the measure preserving action. So we take X, that is kind of nice, as in the previous lemma when we were discussing why this probability Lebesgue space exists. So we take X, which is a locally compact and second countable space. and the G acts continuously on X. Mu is a Borel probability measure on X. And let's assume that mu is preserved by elements of G. Then it's a modeling example of a measure preserving action of G on X. Now we will use this definition describing some of these actions and their properties. So let's see that we have a measure preserving action of G on this Lebesgue probability space, and then we will have an action by isometries of G on the spaces LP X A mu. P can be whatever between 1 and infinity. So it's measured functions whose P's grade is integrable, right? P's degree. So if we have such an action, then we have actions by isometries on these spaces. And the action is as follows. You have f as a function, G is an element of your group, and you consider f composition G minus 1 as a set of LP. So if we want to study the dynamical properties of these actions, we need to understand these representations better. And we need to express properties of these actions, for instance, continuity of actions, in terms of these representations. So one more definition. Let's say that now our space is a Banach space. So you add norm and completeness, and you take a locally compact group. And G acts on E by isometries so this action is strongly continuous if G times E to E is continuous. What do we mean here? It means that we take whatever V in E, and we take G to GV, and G to E. It's continuous at the point E. Now, an example, as usual. At E, it's a, you mean, what does it mean? Here, you take whatever V, and you consider this action. And you want that the corresponding map is continuous. In particular, it should be continuous at the identity point also. So, but this was just an illustration. It's enough to understand this part. So, what is a standard example of it? It's given by the following proposition, as usual, that we have a locally compact group and the probability space with measure preserving action. This is Lebesgue probability space, as we like. Then we claim that the associated actions of G on LP are strongly continuous. One example. So in general, maybe you can suspect that it's always true, but here it's important, I did not write it, but it's important that P should be finite. And if you consider an action of G on L infinity X A mu, it cannot be strongly continuous. And as an example, if it's not a probability space, it's a Lebesgue probability space, it may not be true. So for example, let's consider the case when we have a circle as a space. And we act by translations. So it's a one-dimensional torus that acts on itself, or circle that acts on itself. So it acts by translations, and then we can take whatever interval and consider the orbit map of the indicator function of this interval. The interval should be a proper interval of this circle. And we consider the orbit of this, the indicator function of this interval, and you can see that it's not continuous. So you need to require something. And then one more thing that is important for us. This proposition I will prove, but a little bit later. So we skipped the proof of that one, but this I'm going to prove a bit later. So before we prove it, let us check one more fact that relies a lot on the properties of Haar measure. And then we will use this fact to prove this statement. Lemma. G, locally compact group, B, measurable subset of G with, it's important, finite Haar measure. You remember we spent a lot of time last lecture to discuss in detail the Haar measures. So now we will get some application of it. Then B minus 1B is a neighborhood of E in G. I will prove this lemma first and then apply it in the proof of the next proposition. So lambda will be my Haar measure. I hope you remember the definition of the Haar measure, and you remember in particular that it's a Radon measure. So we can apply this property and say that B necessarily contains a subset with positive measure. And we can assume that this subset is compact. I will recall this, denote by this set by K. So it had a finite non-zero measure. So it was a Radon measure then, and then we have such a subset. And once again, since Haar measure is a Radon measure, then there should be V. It's an open set. That open subset of G that contains K, such that the measure of this V is smaller than two measures of K. So V itself contains K, but V is not much bigger than K. If we take 2K, we will include V. But now I assume that K is compact. Time to use it. So they should be a neighborhood of the identity point in our G such that Ku is a part of this V. Because K is compact, so in some sense it's bounded. So if we take a small neighborhood of the identity point, we consider Ku, we should be inside of this V. But then I claim that necessarily U is a part of K minus 1K, is a part of B minus 1B. Why it's true? Because if I take G from here, and then I consider Kj, and I consider union with K, then it should live inside of V, because this is true, right? So I take G from here, and then I consider Kj, and K, it should be inside of V. And then I can say that the measure of Kg plus the measure of K, which is basically the two Haar measures of K, if it's not included, then it should be greater than this. Because if it's not true, this statement, then Kg and K, for some G, they should not intersect, right? It should exist such a G. And if it exists, then here we have greater. But it cannot be because here we have smaller. So it's a contradiction. And that means that it's true what I announced in the statement. Hmm? Yeah, like if it's not true, if this is not true, then there exists such a G for which I can write all these things. Yes, you're right. Thank you. Now we are ready to prove the proposition. Let's do it. So proof of the proposition. And it's the last thing in our preliminary part. And we will be ready after that to state the Hovi-Moore theorem. So we took F. F lives in LP. And we consider the subset, which is a dense sequence in LP. We can take it, it exists because we have the Lebesgue probability space. So we should have a dense sequence, and then we take a compact set, compact subset of our group with positive Haar measure. So fix epsilon, which is positive, for any h in this LP x a mu. There should exist a natural k such that we can measure the distance between h and hk. And then for natural k, k times x to r, so it's tx f g minus 1x minus hk of x, this is measurable. And thus, we can apply Fubini's theorem. Today, Fubini's theorem will be our main instrument. So it says that then this map given by GF P. This is measurable. And BK, which is a ball given by the conditions that the norm of GF minus HK in the LP. So this is a measurable subset of G. And now we see that our K can be seen as the union of all BK for small k belonging to all the natural numbers. You vary this parameter, and you get as a union the whole K. And then we can be sure that for some value, necessarily this BK should have positive Haar measure. Because key here, it's a compact subset with positive Haar measure. So if it's formed by this BK, one of BK should have positive measure. So now, once we know this, we can apply our lemma that was written here. You see, it's exactly the same framework. So we can say that there exists U such that U belongs to BK, maybe I should write like that, BK minus 1 BK, right? Because it's a neighborhood of the identity, so I can find this neighborhood, and so I can find the subset of this neighborhood. And so what does it give to me? I know that if we take G from this set U that we just constructed, then there should be R and S from BK such that G is constructed as R minus 1 S, because U lives here, so it has such a representation. But additionally, we can use all these inequalities that we wrote everywhere, and so we can see the following thing. Just a second. So GF minus F pi is equal to R minus 1 SF minus F pi. This is SF minus RF, right? And this is RF minus each K. Triangle inequality exists, so we can write this. And each of them does not exceed epsilon, so we can write this one. Why it's true? Because both of our R and S, they live in BK. And BK we defined like that, right? So we can use it when we estimate the whole sum there. And so we can be sure that our map that takes G to GF, it is continuous in 1. And this completes the proof of our proposition. Was it clear? Good. So now we are ready to state our main goal for today, the Hawey-Moore theorem. So we take a Hilbert space that is equipped with a strongly continuous action of SL2R. Now, assume that H, okay, maybe I wanted to require that it's a unitary reaction. So assume that H does not admit any non-zero SL2R invariant vector. Then, for any V and W from the H, the scalar product, it's a Hilbert space, right? So we are allowed to consider the scalar product. This goes to 0, while G goes to infinity. So it doesn't matter whom do you take, these coefficients, they go to 0 when G goes to infinity. So what does it mean? It means that for any positive epsilon, there exists a compact subset K of SL2R such that for any G in SL2R without K, GB W is smaller or equal than epsilon. So in some sense, what can you see here? It's a way to say that our group, SL2R, is very far from an abelian group. Because if you take any abelian group and try to do a similar thing, so you have the same continuous action of some abelian group, and you do the similar thing, you can easily see that it will not be true. It just will not hold. How to see it? Assume that you have locally compact abelian group. Then the characters of this group, so characters, it means that it's a continuous morphism from your group to S1, to circle. So you consider this, and it's known that it separates points in this sense of the statement we did at the very beginning of the lecture. So that there is a function such that you always can distinguish two points. So these guys, they will separate points, and then you take a non-trivial character and consider unitary representation of your group in the Hilbert space, and as a Hilbert space, you can just take this. So you take this, and you consider functions that act from G to T, T1. This will be called a character. This is a Hilbert space, obviously. So you try to apply it, and this action should work by multiplication on this thing. And then this representation does not admit any non-zero G invariant vector, but it's very easy to see that if you consider G1, 1, and you try to compute this scalar product, then it always has a modulus 1. So it never goes to 0. So what I want to say is that if you take an abelian group, then there is some very standard technique in representation theory that tells you that the statement is not true. So it only holds for very non-abelian groups. And it's a way to say that we don't have abelian property in SL2R. Of course, there are more easy ways to check it, but it's kind of explains why its nature is different. Now, I suggest you the following strategy. Since you are probably a little bit tired from all these abstract exercises, I will state now a general version of this theorem, and we switch immediately to dynamical applications. And then we go back and prove this theorem, because I'm afraid that you will be disappointed if I catch you now with all the technical details. So. So now I first state the same theorem for SLDR. It will not be that much different. You take Hilbert space. Equipped with a strongly continuous unitary action. Of SLDR. And we assume, as before, that we don't have any non-zero SLDR invariant vector. Then, for any V and W in H, GV W tend to 0 when G goes to infinity. The same thing, just the same. And now the full version, fully generated. We will not prove it at all, just for your information. Now you have a connected simple Lie group. Instead of SL, you switch to an abstract framework of Lie groups. And you take a Hilbert space, as usual, with a strongly continuous unitary reaction. Then I'm not going to write it up, but you have to repeat the same thing, that if it does not admit any non-zero G invariant vector, then this condition should be true. Okay? It's clear, the statement. Great. Now let's go for dynamical consequences. And then we prove it in the low-dimensional case. So we interpret the results in ergodic terms. We fix the probability space. And we consider a measure preserving transformation. So I recall you, what does it mean to be ergodic? Ergodicity means that all the invariant sets, so those that are T minus 1A coincides with A, they all have full or zero in Lebesgue measure. In different words, maybe you remember when we were discussing the ergodic theorem, we already used it even. So, DCT. There is another expression that we considered the isometry from F to F combination with T of L2 X A mu. And so this does not admit any invariant vector besides the continuous function. It's the same thing to say this is the same as to say that it's ergodic. So, and I recall you also one definition that we already touched, the definition of the strong mixing. You remember we discussed that interval exchange transformations, they are ergodic typically, never strong mixing, but very often weak mixing. So strong mixing, it just means that we consider a measure of T minus NA intersection with B, and this measure in César sense is mu A, mu B, for any two measurable A and B. So what is a corollary from our Hovi-Moore theorem is just we take G in SLDR and assume that this G is not contained in a compact subgroup. Then, what do we know? That x to gx of this map of SLDR factor SLDZ is mixing for the SLDR invariant measure. You see, I promised to show you that we can apply these things directly to some dynamical problem. So now indeed what we have is that we have an element of SLDR and it is not contained in any compact subgroup. Then this action is necessarily mixing. The definition of mixing, of course, depends on the measure, and it's the SLDR invariant measure. Now let's prove this statement. At that moment, we believe that Hovi-Moore theorem is true, and we will apply it. So what do we need to prove, since we can use this definition, right? We need to prove that the only invariant functions are constants. Let's try to do it with the use of the following lemma. Lemma. So G locally compact second countable topological group X A mu is a Lebesgue probability space and we keep it with a measure preserving G action. Then we have a measurable function on X such that for any G, the composition phi G almost everywhere coincides with the phi itself. And then it's a very crucial moment here that will explain you the spirit of homogeneous dynamics as it is. It means that we can replace it by a measurable function phi 1 on X such that it coincides with phi almost everywhere. But this condition is satisfied just everywhere. You see, this is the crucial point. The fact that we can replace almost everywhere by everywhere. When we work with tools from ergodic theory, we always can only obtain almost everywhere statements. You probably already noticed it when we were working with the Teichmüller theory or with the geodesic flow. Also in your own research, maybe you saw it. But very often we need a statement that would be true for some particular subset, for some subset of measure 0, for one surface, for one element of dynamical system. And then all the theories that deal so successfully with one interval-exchange transformation, but all the theories that tells us what happens to almost all of them fails. And so in these cases, the only way to prove something is to get a tool that would lead us to the everywhere statement. And that's why homogeneous dynamics exists, because it develops tools that allows us, in some particular situation, replace almost everywhere by everywhere, and then use it to get maybe still ergodic statements, but already in a much stronger way. So now we will check it, but I think you already start to understand why do we care about this part of math. Let's prove the lemma. So we take a right Haar measure on G. And we take the subset of the triples GHX in G such that phi does not distinguish GX and HX. Now, as I told you, today I'm very obsessed with Fubini's theorem. So I will use it. What does Fubini tell me? Yes, so, all right, I messed up with brackets. G and H, they are in G. X is an element of X. If you want it, GX. Because I want phi to act on X, G acts on X, phi, so yeah, this is what I want. And now we can apply Fubini's theorem and consider the set of X such that for lambda times lambda, almost every GH in G2, phi GX is equal to phi HX. So this set I will denote it by A. It's a measurable subset. And this subset has a full measure. With respect to the measure mu. Because what we know is that for any G, phi G is the same as phi. So if I apply phi GX, it gives me X. So if I consider in a similar way H, I would have the same thing. So now if I fix this condition and I only consider the projection of this set to X, I will have a subset of a full measure. That's what Fubini's theorem usually does. We have something on the product of two sets, then we can project it and make some measure statement on the projection, right? So that's what we have here. And since lambda is right invariant, because it's a higher measure, so thus the same is true for this set, it's G invariant. Now, if we fix some element of this subset, and we will consider the function already on G, that will take an element on G and apply it to X, and then consider phi of G of X, then this map will be almost everywhere constant on G, if X belongs to this A. So what is this phi 1 that I want to construct in my statement? Since it's constant, then it takes some constant value, right? It has some value, some constant. I will take this constant, and I will say that phi 1 of X is equal to this constant, just everywhere. Now it's the way how I defined it on A, but I also have other points in X that do not belong to A, and so I will say that phi 1 is equal to 0 on the complement. Now I have a function phi 1 which is defined on the whole X. So what can we say about it? I'd claim that it's necessarily G invariant function. And also it's true that we can apply Fubini once again and say that for mu almost any X is from X, lambda, for lambda almost any G in G, phi Gx is equal to phi X, and phi 1 of X is equal to phi of X. Let's check that I don't cheat you. So you believe that we have a function that is defined everywhere on X, because I defined it on A, and then just put 0. Now what can we say? That this should be true on X, because it should be constant everywhere on X, almost everywhere on X, and it's the same constant, right? So it's on A, it's definitely true. This. But what can we say when we are outside of the set A? But A is a set of full measures, so I don't care what happened outside. I put here almost everywhere, almost everywhere. So maybe it was not 0, but we can ignore it, right? Good. So then this phi 1 will be good enough, because phi 1 composition with G is always equal to phi 1. Do you agree? Because on A it's guaranteed by this condition, and outside of A it's always 0, 0 does not change. So we constructed such a phi 1 and proved this theorem. So this lemma is done. And now we have to check that if G from SLDR it does not belong to a compact subgroup, then its power goes to infinity. In general, it's not hard to do it just by the tools of linear algebra. You make Jordan decomposition of your matrix, and then you understand, you take a Jordan cell, Jordanov нормальную форму. The statement, so what do we need to prove here? We need to prove that it's mixing. What does it mean to prove that it's mixing? It basically is the same thing as to prove that if we have a G that does not belong to a compact subgroup, then its power goes to infinity. In general, you can just say that it follows directly from Jordan decomposition. right? Because you consider a Jordan normal form. If you have ones on the principal diagonal, then say 2 by 2, you can say how the power looks like. You can consider a power only for the Jordan cell, and then multiply on the left and on the right, on C minus 1 and C as a transfer matrix, and that's it. But I will not do that, because I want you to understand the kind of what to do if you are not so lucky to work with SLDR. So I will show you some more abstract approach, even if in reality you could do it much easier in this particular case. So, lemma. We have a locally compact topological space. We have continuous map. In general, you can replace it by continuous semi-flow. And we assume that for all x of x, the orbit we will consider a semi-orbit, only look to the future. So n will be non-negative. Here you can replace it by a continuous version when you don't have the discrete orbit, but phi t of x when t goes to is in R plus. So if this thing is dense in x, then x is compact. So I will prove the result only in case of the orbit. For semi-flow, you can generalize it easily. So let us consider a compact subset of X that contains some non-empty open subset. U. Then we assume that this guy is dense, this orbit. So for any x at some point, we should enter this U, right? So there exists n. Tn of x is inside of U. For x, let us consider the tau of x the first moment when it happens. It's like the first return map to this U, more or less in the same spirit as we did in Poincaré recurrence theorem. So it's a minimum among all the n when we enter this U. What can we say about tau? it can be seen as a function of x, right? On the one hand, our U is open. So you can be sure that tau is an upper semi-continuous function. In particular, what does it give to us? We did not use yet that y is compact. So if we have a upper semi-continuous function, and we consider it restriction to the compact subset, then it should be bounded. Thus, we know that tau is bounded on y. So if it's bounded, then we can consider the union of all the images of y. But since we always go back to this u, we can consider not the infinite union of these images, but the finite union of them. Because after a while, after some controlled number of steps, we will be back to u. So we will not get completely new points, right? So we can write this. But this person, what can we say about it? This is a continuous map, continuous image of the compact set. So, and we have a finite number of these images in this union, so it's always compact. Right? So, it is also stable by T. It is stable by T, but then, and it's a compact set. T is a continuous map, so it should coincide with X. But this means that then X is compact itself. You understand why? Because we understand why it's stable by T. Because you apply it and here there was an infinite union, so it doesn't change anything. So it doesn't move when you apply T. But T cannot have some non-trivial stable subset. So it should be X itself. So X is compact. Now we can extract a corollary from this statement. If you are not too tired, maybe we skip the break and I finish earlier today. It works? So let's extract a corollary, and then we will be back to the proof of this mixing statement. So G is, as usual, locally compact group. And it's an element of this group. And we assume that its image under the action, so it's Z orbit is dense in G. Then I claim that there are two possibilities. Either G in reality is this orbit, either G is compact, as in the previous statement. So how will we prove it? Assume that G is not the orbit, because if it is, it's not interesting, we are done. So we assume that G is not equal. And we will prove that then it should be compact. then if it's not discrete, then for any neighborhood V, of the identity element, of the trivial element, for any integer n, non-negative, there exists another integer such that GP is in V. Because we said that it's dense. So we should enter any neighborhood. Then it means that for any neighborhood we will enter at some point. And moreover, we will do it quite regularly. So why it should be true? In general, the fact that we enter follows from the density. Why this condition holds? We can assume that V is symmetric. And since G is not discrete, then we can remove the points GK from V when K is between minus n and n. And if we consider such a subset, then it has non-empty interior. And thus, it should contain, if it has non-empty interior, then by the density argument, there should be some element of our GP. Sorry, here it's P. And since V is symmetric, we can say that we can put modulus here, and so we can assume that it was a positive P. So now, then we are done. So now I am going to prove that if this was dense, then if I restrict myself just to natural numbers, so it's a semi-orbit, then this semi-orbit will be dense as well. It follows from what we just discussed. We take some open subset U of G, and then there should be some K, the integer, not necessarily positive number, such that GK will live in U. But if we do that, then we can consider a neighborhood of the identity such that VGK is in U. And then we will apply this argument and take P, which is greater or equal than modulus K. And so then we should live in V, this GP. So what we got is that G, P plus K is in U, and P plus K is non-negative. So it's okay that we restricted ourselves to semi-orbit and not to the whole orbit. Thus, we can apply that lemma to say that our group is compact. Then if it's clear, then we are ready to finish this proof about mixing part. Was it clear? Good. So, end of the proof of this mixing corollary. So we consider the natural action of SLDR on the space SLDR factor SLDZ. We take an element of L2 SLDR factor SLDZ. This element is SLDR invariant. So what does it mean? It means that our function admits a representation that is SLDR invariant function. Now, what can we say about the action of SLDR on this quotient space? We can say that this action is transitive. You remember transitivity means that we have some dense orbit. But once we know that we have some dense orbit, then we understand that we move somewhere to this framework that we just discussed. And so we can be sure that in reality we deal with a constant. So this function should be a constant, right? And then the space of functions with zero integral in SLDR factor SLDZ does not admit any non-zero SLDR invariant vector. So the mixing property now follows from our favorite theorem. Up to now we have not applied yet the Hovey-Moore theorem, right? So do you still remember what it is about? It was about some coefficients. So by the corollary that we just proved, we said that for any G in SLDR that does not belong to a compact subgroup, and for all these guys, what we have is that Gn goes to infinity in SLDR. Right? Do you understand? It follows from the Hovey-Moore theorem. So if it goes to infinity, then we are done. It's exactly what we wanted in mixing statement. So in SLDR, in general, you could apply just the Jordan decomposition and work with linear algebra. But if you want to get an idea how to move it to a more general framework, you should execute this strategy that could be executed also in a much more general framework. And I hope it was clear that this Hovey-Moore theorem that at the beginning looked as something from representation theory or functional analysis, in reality leads us directly to ergodic statement, to the fact that some action is mixing, right? So now we have to prove our theorem. Let's try to do it. It should not be that long, because we already did a lot of preliminary work. So it will take us, I think, maybe 20 minutes, maybe less. So to prove the theorem, I will prove it in SL2R. This thing I did for SLD, but the proof I will show you how it works just for SL2. So we will do the following thing, that we will use so-called Cartan decomposition. We fix the following notations. You remember last time we considered the different decompositions, Iwasawa decomposition to prove some statements in order to get the statement that SLDZ was a lattice in SLDR. Today it's time to make another decomposition, and let's try to do that. So A plus will be the set of diagonal matrices. With the positive entries in SLDR. such that we can order the diagonal elements. A11 is greater than A22, and so on. ADD, inequalities are not strict. And then our Cartan decomposition says that SLDR can be seen as K. It's the one from this KN, AN previously, you remember. The one that we used the last time. K was SOD. We had K, N, N. Now A we replaced by A plus. And I say that I can write K, A plus, K. So more precisely, for any G in SLDR, there exists and unique A that lives at the intersection of A plus and KGK. What does it mean to have such a decomposition? So here, this proposition follows from some very natural linear algebra. Namely, I suggest you to do the following thing. Take G. Consider GT G. It's a matrix, right? And it's a symmetric matrix. And moreover, it's a positive one. So probably you studied in linear algebra that then you can define a square root from it. So we can say that S is a square root of this matrix. So we can say that G is Ks with K as an element of this SO. It's just the way how you prove the existence of the root in linear algebra. So the existence of decomposition now follows from the fact that S can be diagonalized. And the uniqueness comes from the uniqueness of the square root. Now, once we have this decomposition in mind, let us complete the proof of the Hovey-Moore theorem. So proof of the theorem. We fix V in our Hilbert space. And we have to prove that GV goes to 0 in H when G goes to infinity for the weak topology, right? That's our goal. We will apply a famous theorem by Banach, Alaoglu. So what does it say? It says that a closed unit ball of the dual space of a normed space is compact in a weak star topology. So this theorem guarantees us that the closed balls of H are weakly compact. So in order to prove this thing, it's enough to prove that all the weak cluster points of GV, so all the local limits, are 0, right? Because it's weakly compact. So since SL2R, it's a nice space. It's a second countable. So maybe we will need to replace our H by the closure of the subset spanned by SL2R V. It is sufficient to prove the following thing, that for any sequence GP that goes to infinity in G, if GPV goes to U weakly, for some U from our Hilbert space, then U is 0. That's what we want to prove. And if we have this, that will be enough for us, right? To complete the whole statement. That if there is such a limit, in a weak sense, then this limit is 0. So now as we take this U, V, and GP as before, and we take P. P is not whatever, it's a matrix. So we can GP. And so we can take, we take P and we take GP, and for GP we can make a Cartan decomposition because GP is a member of SCR. So we can say that our GP is KP, AP, LP. But then AP goes to infinity. If GP goes to infinity, then AP has to go to infinity because these two guys, they live in SO. D, they cannot contribute that much. So all the big norm should be included here, so it should go to infinity in A plus. So maybe we will need to extract a subsequence, but we can assume that KP goes to some limit and LP goes to some limit, right? Because it's sequences, they're bounded, so there is a convergence of sequences. So there are some K and L, these limits, they both live in K. So I claim that AP LV goes to K minus 1 U. You follow me? So I have AP, then I take L limit here and apply it to V, as we did here. I cut this first K from here. So if this went here, I claim that I can multiply it all by K minus 1, basically. That I can multiply this by K minus 1. So why it should be true? Why, the proof will be very technical. I will just consider the difference, estimate it, and convince myself that this difference is very small. Let's do it. Еще минут 20, и все. Так. So let's do that. We take whatever P, and we consider the difference. AP, LP, V, KP minus 1 W, minus AP, LV, K minus 1 W. And try to estimate it. As usual, we can add and subtract the same number. And I will do it as follows. AP, LP, V, KP minus 1 W, minus AP, LP, V, K minus 1 W, plus AP LPV K minus 1W minus AP LV K minus 1W. So first we estimate the first, and then we estimate the second part. It's clear, right? I added and subtracted the same thing, AP LPV K minus 1W. So what can we say about the first person? This one first. We can say that we can replace it by AP LPV KP minus 1W minus K minus 1W. Right? Because this person is the same, and all the difference lives in the second part. So this can be then seen as a, we can replace it by the norm of V times the norm of Kp minus 1W minus K minus 1W. Because APLP will not change the situation that much. We are in SL. So the determinant of the matrix is limited. Now the second part, this one. Here it's the opposite. This guy is the same, and these people are different. So you can say that them are like LPV minus LV. AP I will move to the next. So it's AP minus 1, K minus 1W. So this can be estimated as a norm of LPV minus LV. And here I can write W. So in both situations, it's very clear that since we know that K is the limit of Kp and L is the limit of LP, then in both situations we have that we go to 0. Yeah. Because I moved AP to this part, it changed the position. So it went to infinity. Now, since GP V goes to U weakly, and then we know that AP LPV Kp minus 1W goes to UW, which is K minus 1U, K minus 1W. And so the first statement I made is done. This one, I don't see where, here. What I wrote here is true. This we checked. So now the next step will be done in a minute. So we will now prove that this implies that the following thing. That let me first introduce some new notations. V prime is LV, U prime is K minus 1 U, and I claim that U prime is N invariant. So the N is the guy we introduced last time when we defined this KAN decomposition. You remember? So N is a group of upper triangular matrices with eigenvalues equal to 1. So we fix element here. And we note that for any n, since AP for us goes to infinity, in A plus AP minus 1 and AP necessarily goes to identity. Now we can consider for any W and any P and AP V prime W, this is AP minus 1 and AP V prime AP minus 1 W. And so when we try to estimate the difference, since we want to check this, that's what we do have to check. We have to check the difference between AP minus 1 and AP V prime AP minus 1 W minus V prime AP minus 1 W. So we work hardly and check that this can be estimated by AP minus 1 and AP V prime minus V prime W, and this will necessarily go to 0. So we have no doubts that NAP V prime minus W minus AP V prime W, this goes to 0. And so N U prime W is equal to U prime W. And N U prime is equal to U prime then. So U prime is stable under the action of N. It's clear, the idea. We check it directly. As usual, we estimate the distance. And we conclude it. So now I claim that actually this implies that my U prime is actually SL2R invariant, not only R invariant. And then I believe that if I can check this, then by assumption, you remember we assumed that there are no invariant vectors, so U prime should be trivial, should be 0. So U, which is KU prime, it should be also 0. But then if it's 0, we are very lucky people. We proved our theorem. So we are only missing how to check that this implication holds. So let's work a little bit more to check that this is true. And once we check it, the theorem is proved. So we take phi and consider it as a function on the factor of which is nothing else than R2 without 0. And since we consider this factorization, we say that it's constant on n orbits here. Now, we take y, which is whatever point in R. Let's say that it's not equal to 0. And the n orbit of 0y in R2 is a line So phi is constant. On each r star times 0. Star means that we remove 0. Because we work here, so we remove 0. In other words, is it clear what's going on now? We are checking this thing, so we need to check that our u prime is SL2R invariant. So we consider this function phi. We consider it as a function on this set. And now, what does it mean? That for any pi u prime, which is coincides in the norm, here it's not very accurately written, with u prime square, so that by the equality case in Cauchy-Schwarz inequality, you see we have Cauchy-Schwarz, and here we have equality. So that means that two guys should be equal, right? So we know that then pu prime just coincides with u prime. So u prime is p invariant also. It's n invariant, it's p invariant. So what can we say about phi? That it's left and right p invariant. So we can consider it as a function on a factor of g over p, and this is a projective line. And again, so we say that it's constant on p orbits here, since p orbit of r01 should be equal to you do the similar thing, basically. And then you get that phi is constant. And thus, u prime is SL2R invariant. And we are done. Actually, what we did here can be considered as some algebraic representation of the Hopf argument about the geodesic flow, why it is ergodic. You remember, we made a proof of the ergodicity of geodesic flow. Geodesic flow was given by a matrix, ET0 or TT1 over 2, 0, 0, E minus T over 2, and we checked that this action is ergodic. And the home task is to think why in reality it's the same statement morally. What we proved now with all these manipulations with matrices, that it's not that different from what we did there with the geodesic flow. Think about it just to put it in order. So we stop here for today. The next lecture will be on Zoom. I will not be in Moscow, so I will give the whole lecture online. I will provide the link in the Google Classroom. And the next lecture will be dedicated to Dani-Margulis theorem. We will continue to study dynamical applications of these techniques that we are learning.